Hello, everybody. I hope that you guys are doing extremely well and not going stir crazy in our, what is this, like week 7 of quarantine? I'm not sure. I'm not really counting days anymore. But anyway, in terms of virtual learning, we are going to be in week 5 this week, and we're going to kick it off by talking about energy and specifically energy and chemical reactions. So let's go ahead and jump into it and get started. So talking about energy, there are different types of energy that we can think about, and there are some examples on the screen right now. So one is radiant energy, so energy that comes, think about like sunlight, radio waves, X-rays, that would be radiant energy, so things that give off radiation. Thermal energy is heat energy. Chemical energy is stored in the bonds of compounds. So we know that chemical compounds can have single bonds, double bonds, triple bonds, and that chemical energy is stored in those bonds and can be released through chemical reactions. Nuclear energy, typically we think about that when we think about nuclear reactors that give us power, right? So, and typically the source that's used for that is uranium, and you can do fusion or fission reactions, and we talked about that back when we did radioactive chemistry. I think that was what in like unit 2. It seems like forever ago now. And then electrical energy, which is the energy from electric current. So let's go back to probably middle school. I think you probably learned about kinetic and potential energy in middle school, but let's just review really quickly the difference between kinetic and potential energy. So we're going to look at this diagram. We're going to imagine that quarantine is over and we have gone out for a bike ride. So we're going to be riding our bicycle up to this hill. And while you are pedaling this bicycle, you are putting energy in. You are in motion relative to those stationary things around you. So you have kinetic energy. Okay, so kinetic energy is energy of motion. So you're putting in all this energy in, you're huffing and puffing, you're getting up the hill, and then you reach the top. Okay, and there's a moment when you're at the top of this hill where you are stationary. This is when you have potential energy. Okay, and potential energy is basically just the energy of position. So it basically means you have the potential to release energy, but you're storing it and you're keeping it and you haven't released it yet. Okay, so when you're at the top of this hill, you've got potential energy. And then, of course, we fall down the hill, you've got your energy output. It's a lot easier to go downhill than it is to go uphill, right? But again, you are in motion, so again, you have kinetic energy. Okay? So if we define potential energy is stored energy. So if we look at some examples of that, like batteries do have chemical potential energy. So batteries have stored energy, right, that we can get out of them. When you buy a pack of batteries, they come in their little like plastic coatings or their containers, and they're not powering anything, right? But they have the potential to. They have stored energy in them. So as soon as you pop them into a clock or Xbox controllers or anything that takes batteries to power your electronic devices, then that potential energy is released and it powers your electronics devices. Some other examples are like springs in a watch. So again, just the energy of position, stored energy, that's mechanical. And then water trapped above a dam has gravitational potential energy. And gravitational potential energy, again, just the energy of position. So it's close to the earth. This dam is held here, or the water in the dam is held here, and then if energy is needed, you can raise the dam, the water will flow through. It will go from having potential to kinetic energy, and typically it'll spin a turbine and generate electricity. So potential energy can depend on a few different things. Number one, the type of atom you have. So we're talking about specifically to chemistry here. The number of chemical bonds and the arrangement of the atoms. It's important to know that whether moving or non-moving, the amount of energy never changes. Only the type of energy changes. Okay, so whether it's kinetic or it's potential, the actual amount of energy in a system or the amount of energy you're talking about doesn't change, just the type. So it can go, when we were looking at our bicycle example, we went from kinetic to potential to kinetic, but the amount of energy wasn't actually changing. And this actually helps us explain the law of conservation of energy, which states that energy is neither created nor destroyed, only transferred. So that's something important to keep in mind as we go throughout this unit. We're never going to be getting rid of energy in any way in terms of it's never going to disappear. It's only going to change forms. Okay, so we can lose energy oftentimes as heat, like it can leave a system, but it's not actually just like disappearing from the universe. Energy can't disappear, it can only be changed. Kinetic energy is your energy of motion, so when you are moving on the bicycle. And there is a formula which is 1/2 times mass times the velocity squared. Okay, so if we look at this, the mass of an object, just how large it is, and then the velocity is the speed. Okay, you guys aren't going to have to do kinetic energy calculations, but it's good just to know about it. So let's take a look at an example with kinetic energy. So it says school bus or bullet. Which has more kinetic energy, a slow-moving school bus or a fast-moving bullet? So if we look at our energy calculation for kinetic energy equals 1/2 mass times velocity squared. Well, for your school bus, you've got 1/2 times 10,000 pounds times 1/2 mile squared. So the school bus weighs a lot, but it's not moving very fast, okay? And then your bullet doesn't weigh a lot. So if we look at it, it's got 0.002 pounds, but it's moving at 240 miles per hour. Okay, so either one may have more kinetic energy. It depends on the mass of the bus and the velocity of the bullet. But which one would be more important? So which would be the most important factor, the mass or velocity? It's going to be the velocity. Why? Because if we take a look just at this equation in terms of how we break it down, the velocity here is squared, right? So anytime that you're squaring a value, it's going to increase pretty exponentially as compared to just your mass, which is you're not squaring your mass at all. So your velocity typically is going to affect your kinetic energy more, is going to be more important than the mass of an object. Okay, so just something to keep in mind. Again, you guys are not going to have to worry about calculating kinetic energy, at least not for us this semester. Yay, quarantine, but just something to keep in mind as we move forward. So another example from potential to chemical or potential to kinetic energy is if we think about fueling a car. So your car is parked in the garage, in the driveway, whatever. You've got gasoline in it, we're assuming that we have gasoline in it. And the gas is stored, nothing's happening, right? If the car is sitting idle, it's not going anywhere, right? So that gasoline has potential energy, okay? And it's chemical potential energy. That chemical energy is located in the bonds of the gasoline, the chemical bonds of the gasoline. So let's say that you need to go somewhere. You've been in quarantine way too long. You're going to make a trip to Walmart. You got your little like COVID-19 mask out and you're going to go get some Oreos or whatever. So you get in, you start at the car and the gas starts to burn. Okay, so no longer is the gas being stored. Now it's being used to fuel the car. So this potential energy is being turned into kinetic energy, right? The amount of energy is still the same. It's just being transformed from potential to kinetic. As the car begins to move, the energy is going to be released from the system in the form of heat, okay? So thermal energy is still a type of energy, right? We're going from potential to kinetic, and we're losing some of that energy in the form of heat, okay? So it's not disappearing from the universe. It still exists. It just exists in a different form, okay? So there are two different types of reactions that we need to know about. The first is an exothermic reaction. So exothermic reactions happen when energy is released. So if we're looking at a chemical reaction and energy is released from the system, then it's going to be exothermic. So think of, if we break this down, exo means out, thermic is in relation to heat. So exothermic, the heat is moving out of the system. When energy is absorbed, it's known as an endothermic reaction. Okay, endo means within, okay, and then thermic again is in relation to heat. So the system is taking on the heat. Just a term to be aware of is specific heat. You'll see it denoted as a lowercase c, and that's just the energy required to raise the temperature of 1 gram of a substance by 1 degrees Celsius. And a lot of times you can find specific heats of substances in reference tables. And there are different factors that will affect the specific heat of chemicals, including mass, temperature, and also energy and heat as well. So the last thing we're going to do today is take a look at energy diagrams, and your independent practice of the day is actually going to be taking a look at these as well. So if we look at this diagram, I know charts are everybody's favorite. On our x-axis, we have the course of the reaction, which is just your time. And then we've got the energy on our y-axis. A lot of times you'll see energy in units of kilojoules, which are kJ, and it's just a unit of energy. So here is a energy diagram showing a reaction, okay? And we're going to learn how to identify some specific things on these energy diagrams, okay? So if we're looking at this, when you've already done balancing equations and whatnot, so if we're having a chemical reactions, remember your reactants are on the left is what goes in, and your products on the right is what comes out, okay? And then here is your activation energy. And then your activated complex will be at the top. And we're going to go through and define all these things as well, so don't worry. But you should remember from biology activation energy, right? That should ring a bell to you guys. So let's define these really quick. So activation energy is the minimum amount of energy that reacting particles must have to form the activated complex, which is right here. Okay, so activation energy is basically just the difference between the energy of the reactants and then the amount of energy it takes to get to this activated complex right here. Okay, so if we're looking at it on our chart, our activation energy is right here. The activated complex right here is a short-lived, unstable arrangement of atoms that may break apart and reform the reactants or may form products. Now, we're going to talk about reverse reactions in a couple days. So basically what this is saying, when it's at this point, it's had enough energy to basically get the reaction going, but at this point, it could either go back and make more of the reactants, or it could move forward and make the products. And we'll talk about reverse reactions later on in this unit. The enthalpy, or the heat of reaction, which is delta H. So delta is a Greek symbol, it just means change. And then that H stands for heat. So anytime you see delta H, it's just the change in the heat of the reaction. So this is the amount of heat released or absorbed in the reaction. So remember, they can be exothermic or endothermic. And then to determine it, you just take the energy of the products and subtract the energy of the reactants. So whatever energy you have here, right? Whatever energy you end up with your products, you're going to take this number and then you're going to subtract the energy of your reactants. And I'm going to show you how to do all of this. I'm going to do some practice problems with you, so don't worry. In an exothermic reaction, remember exothermic, you're releasing energy. So you can identify these pretty easily because when you have an exothermic reaction, your delta H is going to be negative. Okay, so if you're ever looking at one of these and you've got a negative delta H, that's going to be your indication you've got an exothermic reaction, all right? Also, the energy of your products are going to be lower than the energy of your reactants. So if you're looking at one of these energy diagrams and your energy of your products is lower than your reactants, you've got an exothermic process that's taking place. Now see here, our energy is the same. We start with 10 units of energy, and we end up with 8 in our products, and then 2 released probably as heat. Again, the overall number is being conserved, it's just is being changed into different types of energy. And then finally, for an endothermic reaction, it's just the opposite. So if you have your products that have a higher energy than your reactants, then this is going to be your indication you've got an endothermic reaction. Again, your energy is being conserved, right? And in this case, your delta H, or your change in the heat of the reaction, is going to be positive. So remember, endothermic reactions, the system is taking on heat. So think of like melting ice cream. So if you have like an ice cream cone and heat goes into the system, it melts. You've got an overall conservation in the amount of energy, just the type of energy is changed.